everyone, welcome back to the Tox Lab. I'm Rebecca.
I'm Rob. This week we're going to do something a little bit different. I'm often told, I don't know if you get this, Rebecca, as well, having your own science podcast, quite self-indulgent. Well, we're going to take it to the next level, and we're going to talk about some of our own science on the science podcast.
I'm very excited.
So we're going to be looking again at the subject of nitazenes, novel opioid drugs that have been emerging in the drug markets over the last 5 or 6 years, but much more significantly in the last 2 or 3 or so. And we're going to be looking at how they break down, what that means, and why possibly we should care.
Before we jump into today's episode, if you want to stay up to date with our content or get in contact with future episode suggestions, you can find us on Instagram at @the_tox_lab. We also have a page on LinkedIn. And for those of you who don't use social media, you can email us at thetoxlab@gmail.com.
So, Rebecca, our first paper this week, rather excitingly.
I'm very proud of this.
Why don't you introduce us to our first paper?
So the first paper we're looking at today is a piece of work that we very recently published in the Journal of Analytical Toxicology, looking at different metabolites of protonitazene.
So protonitazene is one of the nitazene drugs. So it's a very, very potent novel opioid, 200 or 300 times as potent as morphine, estimated.
About that.
Thereabouts. So very, very significant. And it was an opioid drug that had been emerging in clinical work, in post-mortem work across the UK. And there wasn't a huge amount published on its breakdown. There was a couple of papers that had done liver microsome models. So they had taken a cell line of liver cells, incubated it with protonitazene, and looked for the breakdown products which were formed. But there was very limited real-world data, wasn't there? There was previously published a single or a pair of cases in which some metabolites were looked at in urine. And so we had a fairly large data set. We had seen protonitazene in a number of cases. And we thought, let's apply the same rationale and look at our data to see how many metabolites were present in that data set. We talked a little while ago about high-res accurate mass spectrometry and how that acquires a lot of data in the background that we don't normally look at. And so this was just retrospectively mining cases we had already analysed.
And so we looked for N-desethylprotonitazene, 5-aminoprotonitazene, 4-hydroxynitazene, N-desethylhydroxynitazene, and hydroxyprotonitazene.
A lot of very long words in that list.
It is.
So in other words, we figured out what the masses for these metabolites should be. We knew what their fragmentation pattern should be based on either previously published data or predicted it, and then dove into the data to see which metabolites were present in each case.
So across these different cases, we had a mixture of blood and urine, and we'd analysed them using our very general extraction aimed at extracting like neutral and basic drugs. And then we also developed optimised extraction for nitazenes.
This was something we had done a little while previously, hadn't we? We were aware that our regular extraction method was just not clean enough. We were not getting the limits of detection we needed for these very potent drugs. And so we were using effectively a 2 extraction system.
So across our blood samples with our routine extraction, we were mainly seeing 5-aminoprotonitazene and N-desethylprotonitazene. And in our optimised extraction, we were seeing both of those, but we were also seeing hydroxyprotonitazene, which at the time, and still today, as far as I'm aware, has never been reported in real casework. It's only been seen in liver microsome models.
So the liver microsome models has seen this, so it possibly is a metabolite.
In our urine samples, we were seeing N-desethylprotonitazene and 5-aminoprotonitazene, but we were also seeing hydroxy metabolites, so 4-hydroxynitazene and N-desethylhydroxynitazene. And when using our optimized extraction, again, we were seeing 5-aminoprotonitazene, N-desethylprotonitazene, 4-hydroxynitazene, and hydroxyprotonitazene.
So a range of different metabolites across the range of samples, different matrices, different extraction procedures. Were there any patterns?
So it seemed that the 5-amino and the desethyl metabolites were seen most often across both blood and urine and both extraction methods. The hydroxyprotonitazene that hadn't been reported previously was seen in the majority of cases in both blood and urine on that optimized extraction. Whereas with the 4-hydroxy metabolite and the desethyl hydroxy metabolite, you were only really seeing them in urine. I think we saw them in like one case in blood, but mainly they were detectable in urine.
And this is consistent with more polar or more processed metabolites occurring in the urine.
And it is important to mention that routinely we don't hydrolyse our urine samples, which a lot of other labs do. So it might be that we would see other metabolites in the urine that we weren't able to detect because of the way our work was done. Like, this was all a retrospective data analysis, so no extra analytical work was done.
Yeah, that's completely fair. Are there then glucuronide metabolites being formed later on that we simply wouldn't have seen in this case? I guess the important question is, why do we care?
Well, there was one paper that came out a little while ago that looked at metabolites of protonitazene and said that we should be screening for 4-hydroxynitazene because that's the most common metabolite you detect, and you see quite nice peaks for it across different samples.
This was based on a 2-sample analysis.
Yeah, whereas in our data, we've shown that you don't really see the 4-hydroxy in blood. You see it most often in urine, and even then, I think it's only present in about half our cases. And the metabolism, or the metabolites we see across all these different cases, seem to be so variable, we couldn't see a pattern. Bearing in mind our data set is still quite small. So it seems that you can't get away with just screening for 1 or 2 metabolites. You want to be looking for as many as possible to increase your ability to detect protonitazene exposure.
Yeah, I think that was really the key finding here, wasn't it? That there wasn't an obvious relationship between the signal based entirely, this is entirely crude, based on peak area, the signal of protonitazene and any of the metabolites. There was so much variability. Some cases there was more of one metabolite, some cases there was more of another. Potentially a few factors, differences in stability, potentially differences in individual metabolism.
So I think it was in the liver microsome models, they were looking at sort of enzymes that produce these metabolites. So you've got enzymes like CYP2D6, CYP2B6 and CYP2C8, which are known to be highly polymorphic, so could potentially account for the variability we're seeing across cases. But there are so many different factors. You've also got to account for potential post-mortem redistribution. We've talked about this before. We don't know how nitazenes behave in that post-mortem interval.
We have some idea that they're possibly not behaving in a way that is nice.
So depending on how long that interval is, that could potentially account for why you're seeing some and not others because of just the way they're redistributing.
And then layer on to that, obviously post-mortem redistribution of the metabolites themselves could well behave in very, very different ways, almost certainly will, given that some are much more polar than others. I think that takes us on to a key point, doesn't it? If there is a lot of genetic variability for how these nitazenes are metabolized, and crucially, some of these metabolites are active, aren't they?
Yes, so we know that N-desethyl protonitazene and 4-hydroxynitazene are active, although less so. So N-desethyl protonitazene is about 3 to 6 times less potent than protonitazene, and the 4-hydroxy is between 80 and 160 times less potent than protonitazene. So while still active, they are less potent, but the other ones, so the desethyl hydroxy, the 5-amino and hydroxyprotonitazene, there is no potency data out there as of yet. And one of these could potentially be slightly more active than the other ones and could therefore potentially contribute towards toxicity. We also don't know how well they cross like the blood-brain barrier, for example, and therefore like how well they're going to act even if they do reach the receptor and things like that. So
yeah, that's really fair, isn't it? That's another quirk of some of the nitazene metabolism. We saw this with isocinitazene and N-desethyl isocinitazene, didn't we? Whereby N-desethyl isocinitazene in cell models actually had higher potency at the receptor. But in animal models, that wasn't quite the case. And we think it was to do with it was more polar, so it wasn't quite crossing into the blood-brain barrier in quite the same way as the parent drug was. So this does all complicate interpretation of potential toxicity, doesn't it? If you've got a drug behaving differently in different people, potentially you might see different results from a similar dose.
Yeah, it is quite messy. And another thing, we've seen it with N-desethyl isonitazene. N-desethyl protonitazene is emerging as a drug in its own right, as well as a metabolite of protonitazene. So when you see it, you can't always be sure whether it's there because it's as a metabolite of protonitazene, or whether it's also there because it's mixed into the drug supply, and that also complicates interpretation further.
Yeah, that's another good point as well, actually. And the amino as well. 5-amino isotonitazene emerged as a drug in its own right. I'm not aware of 5-amino protonitazene yet, but there's no reason it couldn't.
Very true. So there are some important caveats with our data set. One, for a lot of these, the 5-amino protonitazene, the desethyl hydroxynitazene and the hydroxyprotonitazene, there are no reference standards available. So when we're saying they're present, it's purely based on accurate mass, based on the pattern of fragments we were expecting, based on how we know nitazenes fragment in our system. So they're not a guarantee. Another important point is that some of these could be present as degradation products within the sample rather than metabolites.
Yeah, I think that's a really fair point, actually. We know, because we went fishing for these off the basis of microsome models, there is reason to think they will be produced as metabolites, but are they also as a result of either chemical instability or bacterial degradation? Entirely possible. Now, this actually leads us on really, really nicely to our next paper, which we're going to look at today. Rebecca, introduce us to this paper.
So this next paper is looking at the detection of 5-amino metonitazene and 5-acetoamido metonitazene in a post-mortem case. So in June 2023, this lab received samples that were collected at post-mortem for analysis. They received 1 preserved blood sample, 2 unpreserved blood samples, and 1 preserved urine sample. And these were screened using LC triple quad, MS, and they first tested the unpreserved sample and detected metonitazene at a concentration of 1 microgram per litre. So really, really tiny. They then wanted to use their LC cutoff to requantitate this in the sample, and there was a delay of about 86 days between first analysis and the second analysis. And when they tried to look for it on their LC cutoff, they couldn't see it. It was below their limit of detection. They then went and retested all of their samples on their triple quad, and they could see metonitazene in the preserved blood sample, in the preserved urine sample, but it wasn't present in either of the unpreserved blood samples. So they were hypothesizing that metonitazene was being converted into something in vitro in these unpreserved samples.
So it was present in an unpreserved sample. A couple of months later, 3 months later, no longer present in the unpreserved sample. Retested the other samples, the urine, the preserved blood sample, present in both of those. Suggestion, therefore, is it's gone somewhere in the unpreserved blood sample.
Yep. So what they did next I find really interesting. So nitrobenzodiazepines like clonazepam can produce an amino metabolite, and then this can be further acetylated to produce an acetoamido metabolite. But you can also get formation of this amino metabolite through bacterial degradation, and this is highly variable depending on the type of bacteria present in the sample, the storage temperature, whether there's preservative present, and the pH. And so they use this logic to look for both the 5-amino metonitazene metabolite and the acetoamido metonitazene metabolites. And they did this using their LC cutoff and did find both the 5-amino and the 5-acetoamido. And the 5-acetoamido metonitazene had a peak area about 30-fold larger than the 5-amino.
So it does suggest there was some conversion. The fact that the metonitazene disappeared, and then there was the detection of the amino and the acetoamido, hypothesis being metonitazene has become 5-amino and that further converted to acetoamido.
Yeah, and because these were unpreserved samples, you've not got the preservative that's going to stop this from happening. Because they were collected at PM, you're potentially going to introduce some bacteria into your containers, and that's not uncommon. So this all kind of supports this theory. They did also see a possible peak for 5-amino-endozethyl metonitazene and 5-acetoamido-endozethyl metonitazene, but there were very trace amounts and they didn't quite have enough fragments to feel confident in their ID. But again, reference materials for these don't exist, so they are like provisional confirmations.
And 5-amino, well, we were looking at protonitazene, not metonitazene, but we were seeing 5-amino as a metabolite, we think. So it's possible, as we were saying, looking at the first paper, that there could be multiple pathways to formation of these products. Some of these could be metabolites, and some of them could also be bacterial degradation products.
Yeah, it is really hard to unpick. Like, for all of our cases, all of our blood samples were preserved, so that kind of limits the possibility a little bit of the 5-amino we were seeing being through bacterial degradation versus it being present as a true metabolite.
Might make it less likely that it's bacterial degradation.
Based on this paper, we did go looking for 5-acetoamido-protonitazene, and we only detected it in one of our cases, and it was in a preserved blood sample and an unpreserved urine sample.
So it was only present in one, and that sample was preserved.
Yeah. And more recently, because we know these potentially exist as markers for metonitazene and endozethyl metonitazene exposure, they have been in the back of our minds, and in a clinical case actually, we detected 5-acetoamido-endozethyl metonitazene in an unpreserved urine sample. But from collection to analysis, that was all completed in about 3 days, and it was stored at 4 degrees.
Let's just break this down for a moment, because you have just said an absolute mouthful there.
Sorry.
Desethyl, so it was the desethyl metabolite, but it was the desethyl acetamido metabolite of metonitazene.
Yep.
So it's undergone 3 biotransformations at that point.
Yes.
And this finding really did highlight the complexity, didn't it? Because I fully agree with the conclusions of the paper about how this looks like degradation, bacterial degradation in a unpreserved blood sample. The fact that we detected an acetamido metabolite in a clinical sample 3 days after collection possibly indicates there might be more going on in terms of whether it could be a genuine metabolite as well. So lots of long names, looking at lots of different metabolites. And we've touched briefly on why we might care. I think there's still a lot we don't know, isn't there?
Yeah, it's such a messy space, because these could be present as true metabolites, they could be present as products of bacterial degradation, but I think the important thing to remember is that these are only going to be present if a nitazene has been there. So they are really useful as markers of exposure and increase your ability to pick these up. What it really means, though, in terms of interpretation, who really knows? But I think they have their use.
Yeah, I think that's really fair. I think the logical next step for any of this now is, now we've identified these metabolites and we know they're present, the question is, going back to our paper, whereby it was a retrospective analysis of all those cases that were positive for protonitazene, how many cases are there out there where there are metabolites but no protonitazene? Because, of course, we would never have picked that up with our retrospective study. And we have been screening for metabolites since then, haven't we? And I think we've had 1 or 2 cases where we've detected nitazene metabolites but no parent drug. So there is real merit in looking for the breakdown products. And as you say, whether they're true metabolites or whether they're breakdown products due to bacterial contamination, or most likely a mixture of both, it still tells you something about nitazene use. It's such a complex area, isn't it? And it's complex because we go looking. Actually, lots of drugs probably have got really, really extensive metabolism pathways producing 5, 6, 8 metabolites. Most of the time, we don't look, we don't care. But because these are new compounds, because we don't quite know how they behave, we've obviously invested a bit of time and resource in looking for these.
Yeah.
So I guess, what's the take-home message? As always, the question.
For me, it's that we need to be screening for as many metabolites / breakdown products as possible. I think to help us pick up as many nitazene positive cases as we can.
Particularly given the public health drive to try and identify these cases.
Yeah.
I would agree with you. I think you probably do risk generating lots of data that is difficult to interpret. But unless we do that, we're not going to move anywhere, are we? That's always the case.
It's very true. And if it does turn out that one of these metabolites where we currently have no potency data for turns out to be quite potent and possibly important in interpretation, then at least we have that.
Yeah, that's fair for sure. Well, I hope you've enjoyed listening this week. Do check out the papers.
Yep, I'll link those in the episode description below as always.
And if anyone has seen any weird nitazene metabolite behaviour and wants to get in touch, do so. We'd love to showcase some more research like that on this podcast.
Hope you all have an amazing week, and we'll see you next time. Bye!